Okay, so in the previous video said that we would pick up on this video with a practice problem, and this one is related to PV work. Okay, so let's calculate the work in joules associated with the expansion of a gas from 1.2 liters to 3.5 liters at 748 millimeters of mercury. So our equation, all right, if we're talking about a change in volume, will be work equals negative P delta V. Right? So our change in volume, that is our delta V, our change in volume. Pressure is our 748 millimeters of mercury. And so we have all that we need. The only trick is this needs to be in either atmospheres or bars. Okay, so having pressure in millimeters of mercury does not work for us. So we're going to do a quick conversion there. So pressure, 748 millimeters of mercury, and there's 760 millimeters of mercury per atmosphere. So our pressure in atmospheres will be 0.9842 ATM, tracking at the third sig fig. And then our delta V, final minus initial, (3.5 liters minus 1.2 liters gives us 2.3 liters. Okay, so work is negative 0.9842 atmospheres times 2.3 liters is negative 2.26 atmospheres liters, tracking at the second sig fig because we've done a multiplication. Okay, so the question wanted the energy in joules, and we have our conversion of 1 atmosphere liter is exactly 101.325 joules. Okay, so we do a simple conversion here, so negative 2.26, tracking at the second sig fig, atmospheres liters. We're going to put atmospheres liters on the bottom, so 101.325 joules in 1 atmosphere liter. We end up with negative 230 joules. Or better yet, to be less ambiguous about our sig figs, we would say negative 2.3 times 10 to the 2 joules. Right, so work is coming out of the system, so that means that the system is doing work on the surroundings. Okay, so now I'm going to take a step back and we're going to talk about calorimetry in a little bit more detail. Switch to a different color here. Okay, and calorimetry is all based on the law of conservation of energy. So negative Q system equals Q of the surroundings, or vice versa. Okay, the important thing being that the signs are opposite. And with calorimetry, Q of our system is going to be an object or a reaction. Okay, and the surroundings is everything else. So that will include the water in the calorimeter itself. Okay, so talking about constant volume calorimetry, okay, typically what we'll have is some sort of container, and it'll be sealed. Okay, and we'll have a constant volume of water in here. right? And we'll have a thermometer that comes down through the lid so that everything's sealed. We're not losing any heat to the surroundings. Thermometer. Okay, and typically we'll have some sort of stirring device. Okay, and we may have a block of metal or some sort of object, or we may mix things in here as a pair of solutions and measure the temperature. Measure the temperature change. Okay, so the water itself is going to be the main component in our calorimetry. And so it will have its own MC delta T. And then the calorimeter, the heat capacity of the calorimeter is determined in a separate experiment. So we'll just have a heat capacity for the entire calorimeter times delta T. And that delta T will be the same as for the water. Okay, and this Ccal is determined separately. Okay, so that's not usually something that you'll have to figure out on your own. If you are asked to figure that one out, you'll be given enough information to do so. Okay, so let's do a practice problem with this scenario. Okay, so a 30.5 gram sample of, that should say alloy, not allow, at 93 degrees Celsius is placed in 50 grams of water at 22 degrees C in an insulated coffee cup calorimeter with a heat capacity of 9.2 joules per Kelvin. If the final temperature reaches 31.1 degrees C, what is the specific heat of the alloy? Now, a coffee cup calorimeter is exactly what it sounds like. You have a coffee cup nested inside another coffee cup. Okay, so we have insulation. Might help if Dr. Lyon could spell. Okay, there's an air gap between the two coffee cups, so it keeps heat from escaping into the surrounding environment. Okay, so we've got our 50 grams of water, initially at 22 degrees C. Okay, and then we're going to add in our alloy, which is 30.5 grams at 93 degrees C. Okay, and then our T final of the water comes out to be 31.1 degrees. Okay, so our hot metal goes into the cool water warms up, the metal cools down. All right, so we are going to be able to figure out what our heat capacity is. All right, so remember we said that Q of the system, negative Q system, is Q of the surroundings. Okay, so in this case, our system is the alloy block. And Q of the surroundings is the water plus the calorimeter. All right, so we have everything we need to solve for this part. All right, and then we can go through and solve for the specific heat of the alloy. All right, so negative Q of the alloy equals MC delta T for the water plus Ccal delta T for the calorimeter. And remembering that delta T here is the same as for water. Okay, so we'll have negative Q of the alloy equals 50 grams, that's the mass of our water, times the specific heat of water, 4.184 joules per gram degrees C, times delta T, which was our final temperature, 31.1, minus the initial, 22, plus C cal, which we're given was 9.2 joules per Kelvin, and times the delta T, same for water. All right, so when we do that calculation, we find out that Q of the alloy, negative Q of the alloy, equals 1987.44. And through all of our sig figs machinations, we find out that the sig figs stop right there. And that will be joules. So simple Q of the alloy is just negative of that. Okay, so now that I know Q of the alloy, I also know the mass of the alloy, and I know the delta T for the alloy. So C is just Q over M delta T. So Q was negative 1987.44 joules, tracking at the fourth sig fig. The mass of our block was 30.5 grams, and our delta T final was 31.1, our initial was 93. So C comes out to be the specific heat of the alloy, 1.05 joules per gram degrees C. All right, so let's take a look at another example of something we can use calorimetry for, and that's to look at solutions. So when we have 25 milliliters of 0.5 molar sulfuric acid is added to 25 milliliters of 1.2 molar potassium hydroxide in a coffee cup calorimeter at 23.5 degrees C, the temperature rises to 30.17 degrees C. Calculate the delta H in kilojoules per mole of water. Assume the volumes are additive and that the specific heat and density of the solution is the same as water. Right, so when doing this type of calorimetry, we still have the same concept of negative Q system equals Q of the surroundings. In this case, the system is the reaction itself, and the surroundings is the water. Okay, the water of the solutions. Right? So we can rewrite this and say negative Q of the reaction equals Q of the solution. Right, so Q of the solution we can do. So we're told that the volumes are additive and the specific heat and density of the solution is the same as for water. So my mass, so Q equals MC delta T for the solution. My mass I'm told that the volumes are additive and the density of water is 1 gram per milliliter. So if I have 25 milliliters, I have 25 grams. Okay, so my total mass will be 50 grams. So our Q solution will be 50 grams times 4.184 joules per gram degrees C times our temperature change for the water, or the solutions, final minus initial. Okay, and we will find that our Q of the solution equals 1395.364 joules. And through sig figs, we'll find that we want to track at that 9. So since our problem asks for delta H in kilojoules per mole, we're going to convert that real quick. So 1.395 kilojoules. Right, so that means that my Q of the reaction is just negative that. Right, so I'm halfway there. So I have the kilojoules part, now I need the moles part. So coming back to look at our problem, we are given information about the amounts of both of our reactants. And that should be setting off alarm bells in your mind that we should be doing a limiting reactant calculation, because one of these reactants is going to run out, and that will also tell us the amount of water that will be made. Okay, so we need a reaction equation. That's going to come out like this. Okay, acid plus base makes a salt plus a water. Remember that one? So I'm going to go through and figure out which of my reactants gives me the least amount of water. Okay, that's my target product here. So we started with, we're told that we have 25 milliliters of H2SO4. We're going to convert that to liters so we can use the molarity, which we're told is 0.5 moles of H2SO4 per liter. And then our mole ratio with water is 2 moles of H2O for every 1 mole of H2SO4. And we'll find that the sulfuric acid gives us a maximum of 0.025 moles of water. All right, so let's figure out how much water we get from the potassium hydroxide. We have the same volume, but the molarity is different. So 1.2 moles KOH per liter. And our ratio is 2 to 2. And we'll find that the potassium hydroxide gives us a quantity of water slightly more. Right, so remember, limiting reactant is the one that gives us least product and tells us the theoretical yield. Right, so my final bit, my question wants to know kilojoules per mole. Okay, so now I have the kilojoules and the moles, so all I have to do is divide. So delta H of the reaction is Q of the reaction divided by moles of H2O. So negative 1.395, excuse me, tracking at the 9, not the 3, kilojoules over 0.025, and that actually should be a 250, moles of H2O. Gives us negative 55.8 kilojoules per mole. Okay, so I hope you've enjoyed working on these calorimetry problems. They are kind of really fun little puzzles, and we'll see you soon.